So, hello students. Today we will discuss about some of the operating characteristics of the transformers. So, we'll try to find out and we'll learn to find out the magnetizing current and the resistances of the windings of the transformer, losses due to resistances, losses due to the no load current or core losses basically, and then efficiency, and then regulation of the voltages in case of transformer. So let us start with the magnetizing current. So basically the no load current, when the transformer is on no load, so the no load current of the transformer has two components basically. One is the effective component of no load current, which is responsible for the heat dissipation in the core, and second is the magnetizing component of the no load current, which is responsible for the magnetization of the core, right? So these two components are basically related to the core of the transformer. So when the transformer is on no load, even then the current that is flowing in the transformer is which is known as no load current, is responsible for the uh, losses related to the core of the transformer. Now, the no load current is generally 2 to 5% of the rated primary current, right? So this no load current is actually the vectorial sum of IC and IM, where IC is the effective component of the uh, you know uh, uh, no load current. Basically, this is the effective component which is responsible for the heat dissipation in the the core of the transformer, right? And Im is the magnetizing component, magnetizing current basically. Now I naught is equal to IC plus JIM, because this is the real component and this is the imaginary component. Im is the imaginary component. So the magnitude is here under root IC square plus Im square. Now if we see the circuit diagram of the transformer, on no load, so here you have the core of the transformer, and the phi m is the maximum value of flux or mutual flux basically. I naught is the no load current, and V1 is the primary voltage or RMS value of the primary voltage. So the no load phasor diagram of the practical transformer is given here. So you can see that the flux, the mutual flux, is because of the magnetizing component. So that is why these two parameters are in phase to one another. And this V1 basically is the voltage applied to the primary, and it is equal to minus E1, where E1 is the value of the induced EMF in the primary winding. Since this induced EMF, because of the Lenz's law, opposes its cause, that is why it is taken as the opposite to the applied voltage. Now this V1, it appears as it is across the core of the transformer. So the effective component, if we see the core parameters, there are two core parameters: the resistance of the core, if you remember this thing, and the inductance or reactance of the core. Okay, so this is, let us say, R naught, and this is, let us say, R X naught or XC, whatever notation you want to take. So R naught, the voltage here is V1. So the current through this R naught is IC. The current here is IC. So the phase difference between IC, which is flowing through this R naught, and the voltage which is appearing across this R naught is 0. In case of resistance, the phase angle between current and voltage is 0. So that is why IC and V1 are taken in same phase, right? I naught is basically the resultant of IC and IM, so it is taken like this. So phi naught is the no load power factor angle, right? No load power factor angle. So the no load input to the transformer, it is V, means the power basically. The input power to the transformer at no load is V1 I naught cos phi naught, right? where I naught cos phi naught from this phasor diagram you can find out based upon hypotenuse IC is equal to I naught cos phi naught. So it is equal to IC. So it is equal to IC. So this is nothing but the no load losses. This indicates the no load losses, right? And the this component is basically responsible for the heat effect. Okay, heat effect. Okay, so basically the hysteresis and recurrent losses which are available in the core of the transformer, right? Now the copper losses under no load condition. So because the secondary is not connected to the load, so the current in secondary is zero because the secondary is open. And even in primary also, the current that is flowing in is no load current, which is very low, which is only 2 to 5% of rated primary current. So the losses in the primary winding, copper losses in the primary winding, because of the no load current are negligible. So these can be ignored. So that means under no load condition, the only losses that are present in the transformer are core losses or iron losses, right? So, so from here we can find out IC is basically core losses or core loss upon V1, where V1 is the RMS value of voltage applied across primary. You may also find it as V1, you may also find it as VP. P for primary one is generally used for primary, right? This is for the single phase transfer. For a three phase transfer, the per phase will be 3 VI. So it will be divided by 3 here, right? For a three phase transformer, right? And the RMS value of the magnetizing current, what will be the RMS value? RMS value is the peak value of the magnetizing ampere turn. Peak value, or you can also say that the total magnetizing MMF required, total magnetizing MMF required divided by root 2, divided by root 2, because RMS value is equal to peak value divided by root 2. So that is why here the total magnetizing MMF means the peak magnetizing MMF divided by root 2. So this will give me an equation of the RMS value of the magnetizing current. Okay, this is how we can calculate the magnetizing current, where T1 is the number of turns of the primary winding. So either it is T1 or it is TP. It is one and same thing. If you find TP somewhere, so TP is also the number of turns of the primary winding, right? So, so now the peak value of this is the maximum magnetizing ampere turn divided by T1. Okay, so this is the peak value, basically ampere turn by turn. So this is the maximum value. It is the unit is ampere basically, right? So so this equation has been justified here. IRMS is justified here, right? So for a three phase, the same per phase value of the magnetizing current is when you divide it by 3, right? So that is the per phase value here. This is the per phase value. Now, and this is the per phase RMS value of the magnetizing current for three phase transformer. This is the per phase. So this is per phase basically, right? So now let us try to understand it in terms of peak factor basically. So let us understand again the no load current of single phase transformer. So let us assume that the length of the flux path through core. So we have discussed, let us say a core type transformer is there. So in a core type transformer, the part of the yoke means the limbs which have the windings wound over them is the core. So this is the length of the core, L. So LC is the length of the flux path through core. So this is the path followed by the flux within the core. And this is the width, W, width of yoke, this one. So L is also equal to height of the window, height of the window. So Ly is the length of the flux path through yoke. Means the flux will flow means when the flux will exit the core area, it will enter into the yoke and it will flow from here to here. So the total length, total distance followed by flux is W, right? So total flux followed by this is W. So now, let us say LC is capital L, Ly W, right? Okay, so total magnetizing MMF of single phase transformer. Total magnetizing MMF is ampere turns. So total magnetizing ampere turns of single phase transformer is twice 80 core, where 80 core is ampere turns per meter of the core, and 80 yoke is ampere turns per meter of the yoke, right? So basically these two parameters are associated with the flux density. So that this 80 core is basically the ampere turns per meter of the flux density of the core basically, and similarly this is for the yoke. Yoke does not have any ampere turn basically, so indirectly we can find out by using the flux density. So twice 80 core L plus twice 80 yoke. So there are two limbs basically. There are two limbs. So if I'll draw the diagram once again, let us say for a core type transformer, this one, and yoke also has two this twice. So twice of 80 yoke into W. So W is in meter, L is in meter. So 80 is ampere turn, right? Per meter. So 80 per meter into meter cancelled out. So it is ampere turn actually, MMF, right? So 280 yoke into W is also MMF, right? So this is the MMF required for joint C. So the basically the joints, the insulation part or the air gap, whichever is apart from yoke area or core area, is also taken into consideration, right? So that means the MMF is also associated with the area or the part which is other than core and yoke, right? So generally this MMF is only 5% of this MMF, means the MMF associated, the total MMF associated with the core and yoke, उसका 5% जो है यहाँ पे होता है, right? ठीक है. So the values of AT core and DO can be obtained from the BH curve transformer steel. So these are the specifications basically. Okay. So the joints in the magnetic circuit may be taken as short air gaps in parallel with the iron paths. Now the calculation of total MMF is based upon the maximum value of flux density, right? So the RMS value of magnetizing current here will be IMM for magnetizing here, comma RMS is equal to total magnetizing MMF required here. Okay, total MMF required. Okay, so it is by divided by root 2 T1. Okay, where total magnetizing MMF required by T1 is the peak value of magnetizing current. It is the peak value. Which one? This part, this one. This one is the peak value of the magnetizing current. Now magnetizing current, if we replace root 2, because peak factor for a sinusoidal case, the peak factor is Im by Im root 2. Im by root 2. So it is root 2. So we can replace root 2 with, we can replace here in this case root 2 with peak factor, because the magnetization or the magnetizing component is not sinusoidal in nature generally. So the magnetization is not sinusoidal in nature. So we can replace root 2 by peak factor, right? Okay. So in terms of peak factor, we have the RMS value of magnetizing current, which is total magnetizing MMF required divided by peak factor into total number of turns of the primary winding. Similarly, for the three-phase transformer also we can find out. So the core, so for a three-phase winding, so we can use there are three basically three parts where the windings are connected. and two parts of the yoke basically. So the formula will remain same, only this has been changed here. Instead of 2 we are using 3, right? So this is, let us say, 80 node, right? And the total magnetizing mmf required per phase. Now we'll calculate per phase. So per phase में क्या होगा, ये पूरा जो हमने यहाँ निकाला है, this value, this is divided by 3, right? Now the magnetizing current per phase will be total magnetizing mmf required by 3 root 2 T1. So in terms of peak factor, we'll replace root 2 with peak factor. So we have this equation. So using these equations, we can find out the value of, or calculate the value of magnetizing current in case of single phase transformer, or magnetizing current per phase in case of 3-phase transformer, right? So now from here, you can find out the component of the no load current which is responsible for iron losses, means the effective component IC. So IC comma 3. So comma 3 is used to indicate 3 phase. So it is Pi by 3 Vp. So this is the per phase value of this one. So that means we can find out the value of effective component of no load current also if we know the core losses. Similarly, we can find out the magnetizing volt amperes, and by using magnetizing volt amperes, we can calculate the value of magnetizing current. So we know that EMF equation of the transformer is EP is equal to 4.44 frequency T1. So we can use T1 or TP, one and same thing, into 5M, where 5M is the peak value of mutual flux. So here 5M, we know that flux density Bm is equal to 5M divided by AI. So AI is the net core area, right? So it is net core area AI, right? So if we replace phi m with Bm AI in the equation, we'll get a new equation here. This one, this is the equation. So from this equation, we can find out the volt ampere, magnetizing volt amperes. So magnetizing volt ampere will be EP into IM, means the peak, RMS value of the induced EMF in primary into the magnetizing current, right? So this is equal to multiplying both components here. So now 80 naught is basically the total magnetizing mmf required. It is actually equal to magnetizing mmf per meter into length of the path in iron. So let us say length of the path in iron means the flux path in iron is Li. So ATM is the ampere turns of the magnetizing mmf per meter, right? And Li is the total length of the flux path within the iron, right? So this is the total value, basically total value, complete value, right? So if we replace 80 node in this equation with this particular equation, so we will get a new equation which is equal to 4.44 FBM AI ATM Li divided by root 2, right? So what is F here? F is the frequency of the input signal, okay, or frequency of the sinusoidal flux also, right? So now let us find out this in terms of weight of the iron. Now the AI is the net core area, Li is the length of the iron, basically iron core जितना flux follow करता है iron core के अंदर, वो total Li है, let us say. So into the density of the iron, volume into density, right? So from here, you can find out the magnetizing volt ampere per kg. So now dividing this with the density, so you'll get a new equation which is equal to 0.4 FBM ATM into 10 to the power 3. So this is the magnetizing volt ampere per kg. So magnetizing volt ampere per kg and magnetizing volt ampere are the basically operating characteristics of the transformer, right? So from here you can also, by using the magnetizing volt ampere, the magnetizing current is related as magnetizing volt ampere per kg into weight of the core. This is weight of the core divided by number of phases into voltage per phase. So this is a general equation which can be used for a single phase transformer as well as three-phase transformer to find out the value of magnetizing current, right? Similarly, we can find out the resistance of the windings. So let us say that LP and LS are the length of the primary and secondary windings respectively in meter. This is the total length of the primary winding and secondary winding respectively. So let us say RP small rp and small rs are the resistances of primary and secondary winding respectively in ohm. Now RP, what is RP? This is the total resistance basically of the winding. So the total resistance is resistance of one turn into number of turns. So this is the total resistance. So rho L by A, the formula is used rho L by A. So rho LP by AP, AP is the area of cross section of the primary conductor, right? Similarly, AS is the area of cross section of the secondary conductor. So this part, let us say is in the similar case with the secondary winding, RS is equal to rho LS by AS. RS is equal to rho is the resistivity of the material, LS by AS. LS is the length of the winding conductor basically, and AS is the area of cross section. So there are total number of turns are TS. So this is the total resistance of primary winding. This is the total resistance of secondary winding. So now the total copper losses by using these resistance, since the copper losses are associated with the windings of the transformer and hence also known as winding losses, right? Or I square R losses. So the total copper losses are equal to I square R losses of primary plus I square R losses of secondary. From here, you can find out the total resistance per phase. So the total resistance per phase is equal to P total copper losses divided by IP square. So this capital RP, just remember this capital RP. What is this capital RP? This is the equivalent resistance of primary, which includes the parameter of secondary referred to primary. I hope you all have studied the referred values also. So basically the equivalent resistance of primary winding is equal to the resistance of primary winding plus the value of the secondary winding referred to primary, means let us say R2 dash, something like this. Okay, so here we have the primary winding RP plus A square. This is the transformation ratio. Whenever the resistances or reactances or impedance of secondary are referred to primary, all these values are multiplied with the square of the transformation ratio, right? So this will give me Rp plus Is by Ip ka whole square into Rs. Similarly, since we are saying that ampere turns of primary are equal to ampere turns of secondary, if you see this equation, so if you see this equation, this one, so in this equation, so in this equation, so we have Is Ps is equal to Ip Tp, right? Means ampere turn of secondary and ampere turn of primary are same, right? So that is being used here in this equation, this one. So per unit resistance here is IPRP divided by Vp, right? So similarly, we can find out the leakage reactance of the windings also. So in short, I have mentioned here that for a core type transformer, the leakage reactance, the total leakage reactance per phase, this is per phase leakage reactance, okay, of the transformer referred to primary, means now this leakage reactance has been calculated by considering the equivalent circuit referred to primary. What does it mean? It means that all the parameters of secondary winding are considered to the primary winding, right? Means the two circuits have been converted into a single circuit. So the reactance of the transformer is given by this equation, where A, BP and BS, LMT and LS, LC, these are the dimensions of the transformer core and windings, right? These are the dimensions of the transformer core and windings, and they are written here. right? So similarly, we can find out the leakage reactance for a shell type transformer, and the equation is given here, where mu naught is the permeability of free space and F is the frequency of the alternating flux. Okay, and the rest of the things are mentioned here. So similarly, we can find out the regulation, voltage regulation also. So let us see that this diagram here is the diagram of transformer equivalent circuit when referred to primary. Okay. So in this condition, you can see Vp is for primary voltage, Vp dash is the voltage of secondary referred to primary, Rp is the equivalent resistance, Xp is the equivalent reactance. Okay, Rp is equal to Rp small rp plus a square small r s. Similarly, Xp is equal to small xp, let us say, plus a square small x s. So this is these are the equations we obtain by using the referred values. Okay, so the phasor diagram here is of this circuit is given here. This is the lagging power factor phasor diagram. You can see this is the phasor of IP primary current, which is lagging its voltage Vp dash. This is Vp dash by angle phi. Okay, similarly, so this is here IP RP. So that means when this current IP will flow through this RP, so the voltage drop across RP is IP RP, and the voltage IP RP and IP means इस resistance के across voltage और इस resistance के through current, they will be in same phase. So there are two ways to show the phase difference zero. One is that either you draw them in this way, concentric to each other, or you draw them in parallel to one another, right? So here you can see both phasors are parallel to one another. So this means there is no phase difference between these two phasors, right? Now you can see this is IPXP. That means जब ये करंट IP जो है इस रिएक्टेंस से फ्लो करेगा तो इसके अक्रॉस एक वोल्टेज ड्रॉप आएगा विच इज IPXP, और ये वोल्टेज ड्रॉप और ये करंट में फेज डिफरेंस कितना होता है इंडक्टर केस में 90 डिग्री का, और वोल्टेज जो है वो करंट को 90 डिग्री लीड करती है. तो आप देख सकते हैं यहाँ पे ये 90 डिग्री लीड कर रही है, राइट. सो फ्रॉम दिस फेजर डायग्राम, अभी नो लोड कंडीशन में क्या होता है, वीपी डैश और वीपी जो है बराबर होता है क्योंकि ये फैक्टर जो है जीरो हो जाता है. ओके, ये जो है ये इफेक्टिवली नेग्लिजिबल हो जाता है और इसको हम जीरो कंसीडर करते हैं. ठीक है. सो द ड्रॉप इन द सेकेंडरी वोल्टेज में, द ड्रॉप वोल्टेज ड्रॉप फ्रॉम नो लोड टू फुल लोड can be calculated by drawing the phasor diagram which is shown here, this one. Okay, this phasor diagram can be used. So from this phasor diagram we get an equation which is given here. Okay, so you can see this equation, and now this theta, which is the angle, phase angle basically between Vp dash and Vp. Okay, so if this is small, if this Vp dash and Vp, this angle is negligible, very less, so in that case means Vp and Vp dash are same. So in that case this equation will change to a new equation which is given here, right? So now rearranging this equation we get a new equation here by taking this on the other side, Vp minus Vp dash. So per unit value of voltage regulation is given by epsilon Vp minus Vp dash divided by Vp, which is equal to this. Now if we divide this as Vp here and here also Vp, let us say this one, this equation. So this is, what is this? This is per unit resistance, and what is this? This is per unit reactance. Let us denote it with epsilon r and epsilon x. So I have mentioned here. So but if theta is very large, in that case this equation does not hold. This equation does not hold. So the equation which is used in this case is when theta is very large. So in that case this equation is used. Similarly, we can find out the efficiency. Efficiency has the same formula. Neta is equal to output power divided by output power plus losses. So losses here are iron losses as well as copper losses, right? So output power हम क्या लेंगे? आउटपुट केवीए, राइट। और 3 फेज केस में पर फेज आउटपुट केवीए, राइट। सो आयरन लॉसेस क्या होते हैं? दे आर द सम ऑफ हिस्टैरिसीस लॉसेस एंड एडी करंट लॉसेस. And hysteresis losses is basically depends upon a factor kh, frequency of the alternating flux and maximum flux density. Similarly जो eddy current losses होते हैं वो किस पे डिपेंड करते हैं? A factor, some factor ke, a constant factor, and square of the frequency of alternating flux and square of the flux density, right? Bm is the peak value of flux density, right? So kh क्या है? Kh is a factor which depends upon the volume. Volume is a dimension of the transformer, right? And quality of the core material and the units used. Means हमने core material किस quality का use किया है, कितना उसका volume है, उस पे kh depend करता है. That means hysteresis losses somehow somewhere depend upon the dimensions of the transformer. Similarly, ke is the constant factor which depends upon the volume. Remember, volume means the dimensions and the resistivity of the core material and thickness of the laminations and units used. Means here also the dimensions are into scenario. That means the eddy current losses also depend upon the thick dimensions of the core and the lamination, thickness of the lamination used, right? Bm is the maximum flux density in the core and F is the frequency of the alternating flux. So here we can find out by putting Bm. So let us see, Bm is Pi. So iron losses are equal to, by adding these two. Okay, so this is Ph, this is Pe. So by adding these two, we get a new equation of the iron losses, which is here. Now from the equation of EMF of transformer, from the equation of transformer EMF, Bm is equal to this. This is the value of Bm. हम इस इक्वेशन को यूज करें, Vp is equal to Ep. ठीक है, आइडियल केस में Vp और Ep को बराबर मानते हैं और हमने ये इक्वेशन, वेर AI क्या है? नेट कोर एरिया. रिमेंबर, नेट कोर एरिया. ठीक है, तो Bm की वैल्यू निकाली, Bm की वैल्यू यहां रखी और इसको फर्दर सिंप्लीफाई किया, तो फाइनली हमारे पास क्या आता है? जनरल इक्वेशन आती है कोर लॉसेस की, आयरन लॉसेस की, विच इज दिस. So in this chapter we have studied the operating characteristics, which include the calculation of the magnetizing current, the calculation of the effective component of no load current, which is responsible for the iron losses, and we have only also seen the equation for iron losses. Then we have studied the resistances just to find out the total copper losses. So iron losses covered, copper losses covered, right? Similarly, efficiency is covered, and regulation, voltage regulation and reactance is also covered. So this is it for this lecture, and here our syllabus for the unit number 4 is complete. Thank you so much.